Modern enterprises depend on databases to handle vast amounts of structured and unstructured data for seamless operations and insights. This course provides a foundational understanding of database concepts and their practical application in today's data-driven world. This is Chapter 5 of a larger course titled Introduction to Information Technology. And besides an introduction itself, the overall course is designed to bridge the gap between technical IT concepts and their practical application in business operations. Let's look at what we are going to cover in this video. First, we will define databases and explore their advantages over flat file structures. Next, we will examine relational and non-relational databases. We will explore different database hosting environments like on-premise, cloud, and hybrid. We will cover authentication, authorization, and common connection tools. After that, we will delve into the structure of relational databases. We will learn the basics of SQL along with common data manipulation commands. Additionally, we'll understand the purpose of large-scale data repositories such as data lakes and data warehouses for analysis. And finally, we will discuss the importance and types of backups as well as concepts such as replication and snapshots. Let's start with a simple introduction to databases. A database is a system that stores and organizes data electronically. In comparison to flat structures like Excel, a database provides much more flexibility and scalability. Let's just take the example of Excel. Data is stored in a simple flat file with rows and columns, and it's mainly used for relatively smaller data sets or individual users. The more data you add, the harder it becomes to manage efficiently. Complex tasks like searching, updating, and ensuring data consistency become difficult in such structures as the dataset grows. Let's compare this with a database. So in a database, data is stored in tables which can be linked together in meaningful ways. Databases are designed for handling large data sets, multiple users, and more complex relationships between different types of data. They ensure data integrity, enforce consistency, and support scalability. There are two main types of databases. First is relational databases. In fact, this is the database that we were referring to in our previous diagram. As discussed already, the data here is stored in linked tables, and these are the databases that we would most commonly encounter when dealing with corporate business data. RDBMS, or Relational Database Management System, is the software that manages these databases, ensuring data integrity and enabling complex queries. Examples include MySQL, Postgres, and Microsoft SQL Server. Then we have non-relational databases, also referred to as NoSQL. Non-relational databases are designed to handle data that does not fit neatly into traditional tables. These databases prioritize flexibility, scalability, and performance, making them ideal for handling large-scale, unstructured, or semi-structured data. There are different types of NoSQL databases. We have document databases, which store data in document-like structures, for example, JSON. These allow nested and flexible data models. An example would be MongoDB, which is used in web applications and content management systems. We also have key value databases. These store data as key value pairs, making lookups extremely fast. They are best suited for temporarily storing frequently accessed data or caching, processing real-time analytics, and managing user sessions efficiently. An example would be Redis, which is used in applications like Twitter and Netflix for caching and quick access to frequently used data. We also have wide column stores. These are databases that group data by columns within flexible families, which are basically containers for related columns of data. These databases are optimized for high write throughput, which means they're really good at quickly saving lots of new information into the database, and also for distributed scalability, which means they can easily handle more and more data and users by spreading the information across many different computers working together. An example would be Cassandra, which is used in large-scale applications like Netflix and Facebook, where fast writes, fault tolerance, and horizontal scaling are required. Now let's look at where these databases actually live. Databases can reside in different environments, and where they are hosted depends on the specific needs of the business. We have on-prem servers. These are physical servers located within the organization's premises. The company's IT team manages these databases and controls all aspects of their operation. This setup offers a high level of control but requires significant infrastructure. We have cloud-based servers. With cloud-based servers, the databases are hosted remotely, that is off-premise, by cloud providers like AWS or Microsoft Azure. This option is cost-effective because you only pay for the resources that you use, and it allows for easy scaling. The databases are maintained by the cloud providers, relieving the company's IT team of some responsibilities. We also have a hybrid setup. So a hybrid setup combines both on-prem and cloud-based databases. This option allows businesses to keep sensitive or critical data on premises for added security while using the cloud for less sensitive or flexible data. It is a good way to balance control, security, and scalability. And we have virtualized environments. In a virtualized environment, databases can reside on virtual machines that are running on physical servers. This optimizes the use of hardware resources and is a common approach for businesses using virtualization technologies like VMware. And just a quick side note here, we will talk more about virtualization in detail in the next chapter on cloud computing. So don't worry if you don't follow this diagram right now. All we are doing here is RDPing or remotely logging into a VM. And you may recall that we briefly spoke about RDP in the networking section. So welcome to the wonderful world of IT, where every topic is somehow connected. Next, let's look at two topics that we need to understand when trying to connect to a database: authentication and authorization. Before accessing a database, users need to authenticate to prove their identity and ensure security. The most common authentication methods include username and password. This is a basic method where users manually enter their credentials to log in. We also have single sign-on or SSO. This method allows employees to log in once and access multiple systems without re-entering credentials. So for example, a user might log in with their company email to access both their database and email. And we have Active Directory or AD groups. Organizations using Microsoft Active Directory can assign users to groups based on their roles. So a member of the finance group, for example, may only have access to financial records and tables. Once authenticated, users receive authorization defining what they can do in the database. You have read access, so users can view data but not change it. For example, a sales analyst might have read access to the customer database for the purpose of generating reports. We have write access. This is where users can add, update, or delete data. For example, a technical user might have write access to update customer contact details. And we have admin access. So database administrators or DBAs have full control, including managing tables and user permissions. Now let's look at how to connect to a database. Once authenticated and authorized, users need to connect to the database. The method depends on where the database is hosted. Let's look at a few examples. The first one relates to using SQL Server Management Studio or SSMS. For on-prem databases, we can use SSMS for connecting to and managing Microsoft SQL Server databases. We can log into a cloud portal. For cloud-based databases like Amazon RDS or Google Cloud SQL, users can log into the cloud provider's web portal. This allows them to securely access and manage database instances from anywhere. And we can even use Remote Desktop Protocol or RDP. For databases running on virtual machines or VMs within an organization's data center or cloud, users may need to use RDP to connect to the virtual machines hosting the database before accessing the database itself. These were just 3 examples, and each of these connection methods ensures users can securely and efficiently retrieve, update, or manage business critical information. Next, let's look at the basic setup of a relational database. Relational databases are structured in a way that makes storing, retrieving, and managing data efficient. Let's break down the basic setup using Microsoft SQL Server as an example. First, we look at the hierarchy of server, database, schema, tables, and then columns and rows. A server can host multiple databases. Each database can contain multiple schemas. Schemas are like folders within a database used to logically group related tables. Each schema can contain multiple tables which organize related data. And these tables store data in a grid format where the columns define what type of data is stored and rows store individual records. We have primary key. Every table should have a primary key which is a special column that uniquely identifies each record. So for example, in the payroll table, employee ID might be the primary key, ensuring that no two employees have the same ID. We also have a foreign key. A foreign key is a column in one table that refers to the primary key of another table. It establishes a relationship between two tables. So for example, an employee ID column in a department table would be a foreign key, linking each department to its manager in the employees table. This helps ensure data consistency across related tables. We have field data types. Each column in a table has a specific data type that defines what kind of data it can store. Common data types include text, so for example varchar, which can be used for storing names, addresses, etc. For numbers, we have a variety of options like integers or int and decimal. These can be used for storing IDs, quantities, prices, etc. We even have date time, which can be used for timestamps, order dates, pay dates, etc. By structuring a database this way, businesses can efficiently store and retrieve data, ensuring consistency and security. Now, let's do a brief introduction to SQL. To interact with the database, users write queries in SQL, which stands for Structured Query Language. SQL or SQL is a standardized way of managing data stored in relational databases. Microsoft SQL Server uses a specific version of SQL called TSQL, which stands for Transact SQL. With SQL, we can retrieve, add, update, and delete data efficiently. Here are some common SQL commands. We have select, which is used for retrieving data. If we want to get a list of employee names and their next salary payment dates from the payroll table, we can use the following query. So basically select the name, payment dates from the customers table. The next query is insert, which is used for adding data. To add a new employee to our database, we can use this query. So first we mention the table name and fields that we want to insert the data into, followed by the values. And notice that in this particular query, we are not adding the employee ID field for the new employee. Realistically, we would set the primary key to auto increment, meaning that a new unique ID will get automatically added when we insert a new record. We also have the update query, which is used for modifying data. So it's update followed by the table name. We specify the field that we want to update along with the value. And we can also specify a condition, which is shown by the where clause. So in the example, if employee 1001 wants to update his name from #C to #K, we can modify it using the query on the screen. And we also have a delete query, which can be used for removing data. So here, if we want to remove employee 1002's record from the payroll table, we can use the query on the screen. Let's look at some more options for storing data. While databases handle day-to-day operations and transactions, other repositories such as data lakes and data warehouses are geared towards large-scale analytics and business intelligence. A data warehouse is a large, centralized repository designed to store and analyze historical and aggregated data from multiple sources. Unlike a traditional database, which is optimized for real-time transactions, a data warehouse is designed to support business intelligence, reporting, and complex querying on large volumes of data. Examples would be Amazon Redshift, Google BigQuery, Azure Synapse Analytics, and Snowflake. A data lake is a storage repository that can hold vast amounts of raw, unstructured, semi-structured, and also structured data in its native format. Unlike databases and data warehouses, data lakes are not designed for transactional data, but are intended to store data in its raw form, which can be processed and analyzed later. Examples would be Amazon S3 with the AWS Lake Formation, Azure Data Lake Storage, and Google Cloud Storage. Before we close this topic, let's look at two important concepts, that is backing up and restoring databases. Backups are essential for protecting business data from loss due to unexpected failures, cyber attacks, or mistakes. They allow companies to restore their databases to a previous state when needed. There are three main types of backups. We have a full backup. This is a complete copy of the entire database at a specific point in time. It's the easiest to restore but requires more storage space. For example, a full backup of an HR database on Sunday night would include all the payroll records up until that time. A full backup on Monday will include all of Sunday's data in addition to the changes made during the day on Monday. We also have incremental backup. This only saves changes made since the last backup. So if a full backup was taken on Sunday, an incremental backup on Monday only includes data changed on Monday and so on. This saves storage space but makes restoration more complex as we need the last full backup and all the subsequent incremental backups. We also have differential backup. This saves all changes since the last full backup. If we take a full backup on Sunday, a differential backup on Monday will include Monday's changes. At this point, it will be the same as an incremental backup on Monday. But a differential backup on Tuesday will include Monday and Tuesday's changes and so on. This makes restoration easier compared to incremental backups but requires more storage. When restoring a database, IT teams follow a process. For example, if the database crashes on Thursday, they might restore Monday's full backup first, then apply Tuesday, Wednesday, and Thursday's incremental backups to recover all data. And finally, let's look at two other concepts related to backups. We have replication. This is the process of copying data from one database to another, ensuring data remains consistent and available. For example, a company might replicate its HR database to a second server so that if the primary server fails, the backup server can take over. We also have snapshot. A snapshot is a point-in-time copy of a database. It is useful for backups, testing, or troubleshooting issues without affecting the live database. For example, before making major updates to a system, IT might take a snapshot so that they can revert back if anything goes wrong. And that's it for this topic. To summarize, we have explored core database concepts for effective business information management. Here are the key takeaways. Databases efficiently store and organize electronic data, offering advantages over flat files in scalability and access. Structured relational databases use tables with defined relationships, while flexible non-relational databases or NoSQL handle diverse data formats. Databases can be hosted on-premise, in the cloud, in hybrid setups, or in virtualized environments. Authentication verifies users, while authorization controls their actions, protecting sensitive data. Databases organize into servers, databases, schemas, and tables with primary and foreign keys for data integrity. SQL is the standard language to manage and manipulate data in relational databases. Data warehouses analyze historical data, while data lakes store diverse raw data for later insights. Backups and techniques like replication safeguard business data against loss and ensure uptime.